Hi everyone, I am Anubhav Prasad. This presentation is a part of our term project for Graphical and Generative Model for ML course. We will be presenting our work on image generation using PixelCNN, Variational Autoencoder, and Generative Adversarial Network. We are a team of 6 members with names and roll numbers on the slide, and each one of us will be presenting on our work. We begin our project by first understanding our problem statement of image generation. We then decided our dataset and models. References to all the papers are provided at the end of the presentation. I will first present about the dataset that we used. Our first dataset is Fashion MNIST. It consists of 60,000 training examples and 10,000 test examples. Each example is a 28 x 28 grayscale image and there is a label associated with it. There are total 10 classes. Images and the class names are shown on the slide. Our second dataset is MNIST dataset. It is a collection of handwritten digits. It has a training set of 60,000 examples and a test set of 10,000 examples. The digits have been size normalized and centered in a fixed size image. The image is a 28 x 28 grayscale image. Now I will present about the models that we used. We worked with three models. First is PixelCNN, second is Variational Autoencoder, and third is Conditional WGAN with gradient penalty. Now I and Shaunak will present our work on PixelCNN. PixelCNN is an autoregressive model. These are likelihood-based models. They are fully observable, that is, they don't have any latent variables. Key idea of these models is to decompose the joint distribution as a product of tractable conditional distributions. That is, probability of an image is the product of conditional probability distributions, where each conditional probability distribution is given by probability of pixel xi given pixel which came before it. In PixelCNN, the above order is preserved by using masked convolution rather than using simple convolution. Learning in autoregressive model is same as maximizing the log likelihood of the models on the given dataset. We used gated masked convolution in place of simple masked convolution. Gated masked convolution uses gated activation units to model more complex interaction between features. Left path is a vertical stack convolution and right path is horizontal stack convolution. Gated convolutions are implemented by having an output twice as large as channel size and then combining them by the element-wise multiplication of tanh and sigmoid activation functions. Now Shaunak will present about the model details and the result.
Hi, I am Shaunak Mondal and I will be talking about the exact structure of PixelCNN. PixelCNN is a purely convolutional network. All the layers in this network are variations of the normal convolution layer. The input of the model can be of any shape, but it should be same during training and inference. Next, the input is fed to a masked convolution layer. The masked convolution is realized using a combination of horizontal stack convolution and vertical stack convolution to remove the blind spots from its receptor fields. The output of the masked convolution is fed to a sequence of gated masked convolution layer, whose structure has been discussed previously. In all these layers, there are multiple feature maps, which are then converted to a single channel using depth-wise convolution. Next, The output of the depthwise convolution layer acted upon by a suitable activation function gives us the output from the model. The output and the input are of the same shape. Next, we can talk about the receptive fields in PixelCNN. Each layer of PixelCNN has a receptive field that depends on the neighboring pixel. However, the contribution of each of these pixels are not equal in the receptive fields. In fact, the contribution decreases as we move farther away from the current pixel, which is analogous to spatial coherence in the image. The visualization of the receptive fields in deeper parts of the network indicates that deeper layers take into account a larger part of the image. Thus, a sufficiently deep pixel CNN model will be able to take into account the output of all the previously generated pixels while predicting the current output. The inference step in PixelCNN is sequential even though it gets rid of the recurrent layers in the PixelRNN model. We start with an image that is composed only of zero values. Then the output of the network is taken as the output of only one of the pixels. We take the value of that pixel, augment the image and send it back to the model. We continue this till all the pixels in the image are generated. The slide shows the output for some of the sampled images from the PixelCNN model. We can see that it achieves good completions for MNIST dataset. PixelCNN can also be used for image completion. In such cases, instead of sending a image of all zeros, we send the input image but partially masked. Then we use the model to predict the masked pixels. Below, we can see in the slide the result of feeding the masked images. It can be seen that for some of the digits, the output is actually very varied and does not resemble the original image. This especially happens in the case of 9 when we see that many of the images generated, though perfectly matching the masked input, are not actually the original image. This means that Pixel CNN is able to take into account the multimodal distribution and produces high probability values for all the possible images in that resembles the dataset. Some more results for image completions using the other class levels. We can see that Pixel CNN achieves good completions in all the test cases.
So I'll be talking about variational autoencoder. So in VAE we have two parts, encoder as well as decoder. The encoder tries to learn the representation of latent variables and the decoder tries to reconstruct the image from the given latent variable. So if we have an input data X, then the encoder provides the mean as well as variance of approximated posterior such that it is as close to the presumed prior. Then a vector is sampled from the prior and the decoder reconstructs the data from that sampled vector. The loss function consists of two terms. First is trying to minimize the negative log likelihood, and the second is trying to minimize the KL divergence between the assumed prior as well as posterior of Z. Now, sampling is a stochastic process, and therefore we cannot backpropagate the gradient. So, to make it trainable, we use the reparameterization trick. So, what happens in reparameterization trick? We say that Z is equal to mu plus sigma epsilon, where epsilon is kind of a notch sampled from standard Gaussian. So now Z, which was first a random node, now it becomes a deterministic node as we see in the reparameterized form. So I trained the VA model using these configurations, and as we see, the result that we got was quite accurate, and it is fine. So now we will be continuing with disentangled VA. Thank you.
Hello sir, my name is Pauras Meher. So I'll be presenting the code and the results for the distangled V or beta V that we have tried. So understanding what is disentanglement. So basic, suppose we have a image of big red apple. So can we get the generative factor for big red and apple separately? So how will be this useful? So suppose we have images of say small black grape and image of big red apple. These two images. So from these two images, so if we have the generative factor for each of these adjective, we can easily generate the new images, say small black apple. So this is the motivation for distangled v. Now how are disentanglement used in v? So we know that in v this latent vector are actually learned, and like if we are able to disentangle this latent vector, then we will have a greater control over the generated set of images. Like we'll be able to generate images that we actually want. Now understanding the loss mathematics of this disentangled VE. So, sir, the loss function of VE actually has two terms. So in VE, like we want to minimize the negative log likelihood, and also we want to minimize the KL divergence between the posterior and prior of Z. So the same thing can be written in another way. See, we want to maximize the likelihood of x, subject to the condition that the KL divergence between prior and posterior of Z is minimum. So basically, the VA maximization objective can be rewritten as a Lagrangian with a Lagrangian multiplier beta under the KKT conditions, which are similar to support vector machines. So after performing these mathematical steps, the VA beta VA loss becomes uh, the one this mentioned. So when beta is equal to 1, which is it is standard way. So like when beta is greater than 1, it encourages great disentanglement in our generated model. So why this is so? So we can see that here the first terms corresponds to or tries to uh, get get the reconstructed images better, while the second term is trying to get the latent representation of this latent vector. So if we multiply it with a beta or a stronger weight, it will give the by minimizing the loss. The model will focus more on learning these parameters of this latent vector. So during these process, like we are able to learn the disentangled latent variables in a much efficient way. So like now understanding the code behind the code that we have written to produce the results. So these are the set of parameters that I've used for in the our code. So I'll show you the code. So this is the model. Basically, this is the model arc. This is the basic model architecture and the hyperparameters I've used. And this is the preparing the data set. This is declaring the model. Then padding shape. Then here I have created the encoder architecture. Then here I have the decoder architecture and basically the decoder. And here I've created the output layer. Then here is the VAE class I've created, and it has various functions to encode, to compute the latent vectors, then to decode, then the forward pass, the optimizer, the training step, the training data loader, the function to sample image, the function to reconstruct image. Then here is the function to calculate the fidelity loss or the reconstruction loss. Here is the function written to calculate the KL divergence loss. Then this is the beta VAE code I have written. Here the loss now is the beta is multiplied to the KL divergence loss. So this is the training for the VAE and the beta VAE I have done, and these are the set of model parameters during the training process. And like I'm testing the model, so while testing, these are the actual set of this is the fidelity loss and this is the KL divergence loss that I've got, and this is the total loss, and this is the function to plot the two set of images. So going back to the presentation, so as you can see here, I have tried shown the code for z is equal to 2 dimension. And now I wanted to I actually wanted to visualize, so how will the generated set of images look or depend upon the latent space dimension. So for this like I tried different latent dimensions versus the and like got the reconstructed and the sample images for this latent space dimension. So for latent space dimension is equal to 1, we can see that both the sample and the reconstructed images, both are blurriness is involved in both of them. And like when we increase the latent space dimension to 2, the blurriness is slightly reduced, but still but still there is more there is a slight of blurriness. Then for the dimension of z to be 8, we can see that the reconstructed images are now like the blurriness has decreased significantly, and uh, in the sampled images, the now the quality has decreased, but the sampled images are more sharper now. And similarly, if we increase the dimension to be 16, we can see that the sampled images are the quality has decreased, but the sharpness now the sharpness or the edges we can see that they are more sharper. And again the reconstructed images quality is like comparative is again increased. So like but this like if we keep on increasing the latent space dimension, the reconstructed image at a certain point it will again start to dip. The quality of the reconstruct again start to dip. So these are basically the set of observations noted. So we can say there is a clear trade-off for increasing the dimension of a latent vector z. So increasing the dimensions actually helps in reconstructing the image more accurately up to a significant point, and decreasing the dimensions helps in better sampling. So this is because like as higher dimension latent vectors are sampled, the they sample sharper images. We can see that sharper images are sampled for higher dimensions, and the reconstructed quality is like still increasing, but there's a clear trade-off for increasing the dimension of latent vector z. So that was all from my side for the code for the VA beta VA and the generation of the images using beta VA and their analysis. So now we'll see about GANs. Thank you, sir.
Hi, I'm Shanmukh Sanath, and in this presentation, I will be explaining conditional WGAN with gradient penalty, which is third model of our project. And GAN is basically deep learning based architecture. It has mainly two submodels or two parts of it. First one is generator and second one is discriminator. So generator basically generates new samples for a given target domain or the given data set. So it takes fixed length random vector or latent vector as input and generates a sample from a given domain. And discriminator takes input as both real images and the generated or fake images, and it will output a sigmoid output or basically a value between 0 and 1 saying which is real or given image is real or fake. So in conditional GAN, both the generator and discriminator are conditioned with labels to generate class specific images. In general for GAN, there is an issue of mode collapse where the model will generate same images for any given latent vector from a random vector space. So to undo that effect, we have added two losses to the GAN or GAN training, both generator and discriminator losses. So first one is Wasserstein loss. So Wasserstein loss is nothing but a measure of Wasserstein distance, which is minimum cost of transporting mass from one distribution to other distribution. So it's nothing but an work taken to convert a data distribution from one to other. And gradient penalty is to make sure that the norm of the gradients is always 1. So it will penalize the gradient in such a way that its norm always stays as 1. And coming to generator, we can see we use TensorFlow to implement this conditional GAN. So in generator, there are barely 1.3 million parameters which can be seen from the left part of image. And right part just gives overview of the generator where there are two inputs. One is latent vector of dimension 128. Other is label of dimension 1. We'll pass the label through embedding layer, which will give in 32 dimensional output, and we'll have a dense layer after that. And after reshaping the latent dimension into spatial vector, we will concatenate both the image, the latent vector and the embedding label, and we'll pass through a contour transpose network which has a leaky railways activation. So for both generator and discriminator, we use the activations that are recommended in the DCGAN paper. And finally, we get the desired image of dimension 28 cross 28 cross 1. And this is the generic generator pipeline. So we'll pass label through label embedder. So label embedder is nothing but an embedding layer followed by dense network. We will concatenate label embedding and noise, which will be passed through an upsampler or convoluted transpose network, and we'll get an image. So in discriminator, there are a few parameters compared to generator, which has in the discriminator we have 182,000 parameters or 0.1 million. There are two inputs in discriminator also. First one is label, which is passed through label embedding, and we will convert the label embedding to an same dimension as that of image, and we'll have an image which is either real or fake. We'll concatenate both the label embedding and image and pass it through a con2D network. Here also we are using Linkirelu. And finally, we'll get an output saying whether a given image belongs to real space or the original data space. So this is the discriminator pipeline, similar to that of generator pipeline. We'll pass label through label embedder. We'll concatenate the label embedding and input image, and finally we'll pass through classifier giving an value between 0 and 1 as output. So coming to training, we used TensorFlow with GPU enabled and Kaggle kernel for training. And if you see both generator and discriminator laws, they're almost saturated at very start of training. So these are some of the generated images over training. So all the images that are generated are conditioned with corresponding label. In epoch on it started generating some random images, and over the training it is able to generate more realistic images. So this is the final image at 97th epoch. So we trained for 100 epochs. This is almost at the last set of last training step. And coming to conclusion, so to compare all the three models we have experimented, we used a metric called FID. FID is in general used for evaluating GANs. So it summarizes the distance between inception vectors. Inception vectors are nothing but the output of inception with the network. And it will see how the real embeddings and fake embeddings are apart in the Gaussian distribution space. And using the mean and covariance matrix of corresponding distribution of real and fake embeddings, we will calculate FID as mentioned in this formula. So if the less the FID, the more realistic the images are. So if you see conditional GAN has the least FID and almost same as VAE, while PixelCNN have highest FID. So the basic difference between GANs and the PixelCNN. PixelCNN is an autoregressive model. So the basic difference is that PixelCNN try to learn implicit data distribution, whereas GANs and VAE learns exploited data distribution, which is governed by an prior. And VAEs try to minimize. So VAE try to reconstruct an image. So it will take input as one image, and it will try to reconstruct the image using an encoder decoder network. Whereas GANs try to generate image from a latent space, so which is nothing but an unsupervised learning problem. Whereas VAEs is a semi-supervised learning problem. So that's the end of our work, and coming to references. So these are the references for dataset and the three models we have experimented on. You can check out if you are interested more. Thank you.